Okay, so hello everyone. Welcome to the week third tutorial for Advanced Quantum Mechanics and Applications. I am Kaustav Mukherjee. I'm a PhD scholar at IISER Bhopal. Okay, so firstly, I'll solve some of the very basic commutation relations and some eigenvalues that was discussed in the lectures. And then I'll move on to the theme of the assignment, that is based on quantum entanglement, and we will see how what we call as quantum entanglement and what is a mixed state, and we will see for very few sample examples which can help you for your assignments as well. Okay, so I'll begin with first one. So I'll just solve a few commutation relation which are not very tough. These are like basics. So some of you might already have seen from the lectures that these were like an open problems that were given by the professor. So we will just solve to get a basic idea of how you can use these angular momentum operators to get these commutation relation, and then I'll find out the eigenvalue for L plus and L minus operator, and then we will move on to the entanglement part. Sorry. So L plus minus I is usually given in this form, where we have Lx plus minus Ly. Okay. Now what you have to find is, let's say, L plus and commutation with L minus, right? So what you will do here is, so some of the relation that I believe you're already aware from the lectures is that Lx Ly equal to I H cross Lz, and similarly it goes in the cyclic rule. So Ly Lz I H cross Lx, something like this. Okay, so to get the commutation relation between these, what you have to get is, so when you have the same operators, it is obviously 0. So only the non-similar are the ones that are going to stay. So these are the ones that are really easy, and we will go through them very quick. And then we move on to the complex part, that is the entanglement parts. Okay, so we have here minus I Lx Ly. So these are all 0, and you can see that these are essentially equal, just the opposite. So you can have minus I Lx Ly, and this you can use from here, I H bar Lz. So this was the first one. Sorry, there is a twice here. And second one is the more important, which we are going to use to find out the eigenvalues of the L plus and L minus operator, which was also an open question in the lecture. So this is something which can be very useful. Lz. So here we are again going to use the same properties. So Lz. So Lz Lx will be I Ly plus minus I H bar. This will be minus I H bar Lx. So taking the plus minus common, we have in the I H bar. So the H bar. We get Lx plus minus I Ly. So this is essentially your L plus minus, right? Now what we are going to next do is find out we are next going to find out the eigenvalue of the L plus minus operator, which are quite useful. So as we know, these are what your ladder operators in the angular momentum space. So what they do is L plus will increase the ml to ml plus 1, while L minus will decrease ml from ml to ml minus 1. Now how do we get this ml plus 1 and ml minus 1 can be seen through this essentially. So let us have a look at this one. Okay, so I'll just recopy it, it's fine. Okay, so what we are going to use is the commutation relation that we just found, that is your LZ L plus minus. So let's just solve for plus, and you can automatically solve the same thing in the similar way for minus. So as just now we saw that this is equal to plus h bar L plus, right? Now we know LZ, this commutation can be written in this form, L plus minus L plus LZ. So let us operate it on your LML, okay, and see how this actually gives us the ML plus 1 here. Okay, so what we have here is h bar L plus LML. So let's say we don't really know the eigenvalue and we don't really know what exactly it does to the state. So let's assume that L plus, when operates on LML, it gives us some shifted state, but which is not ML. Okay, it's ML prime, some other state, but we don't really know which exact state it is. Okay, yeah. So what we are essentially going to do here, sorry about this, yeah. So let's assume that this is some eigenvalue lambda that we are going to consider. Okay, that is the eigen for this LML prime state. So now when LZ, or let's say L plus LZ operates, so since LZ is going to operate first on it, so what we essentially going to get is L plus, here we get ML h bar LML. Okay, now if you put this thing here, then what we will find is LZ L plus on LML minus ML h bar L plus LML, and we have an h bar on the right, L plus LML. So these two are essentially similar kind, we can take them to the other side. What we get is ML plus 1 ML plus 1 h bar and L plus acting on LML. Now okay, so let's say we do this separately, this part on the LHS. So we have LZ L plus acting on LML. Now as we have considered lambda as the eigenvalue, so LZ L plus acting on it gives us lambda L ML prime. So we don't really know what is L prime here. Okay, now when LZ operates on it, so we have already found out the eigenvalue as lambda, which we are going to find out later on. So when LZ is operating on it, we will get ML prime LML prime. So if you compare this equation, let's say 2 and 1, so what we essentially have is that L prime is going to be ML plus 1. From, if you equate the two, then you can write it as lambda ML plus 1 h bar LML plus 1. So what you can see here is that L plus essentially increases the ML part. So it's the angular quantum number, the azimuthal angular quantum number, it increases by 1, and similarly for L minus you can see that it decreases by 1. Now in order to find this eigenvalue, which which is one of the significant part which is used widely in the whole quantum mechanics for hydrogen atom or any other cases, so this can be very useful. So let's say we operate the L plus on the left with the L plus dagger. Okay, so this will essentially give us the same lambda L plus 1. Okay, so now our job is to find the lambda. So how do we do it? So you know that L plus dagger is essentially your L minus. Okay, so what you do is you find out L minus L plus, that is expectation value of L minus L plus, and that will give you your plus 1 lambda square ml plus 1. So this can finally give us the lambda square. So what is L minus L plus? So let us look at this. So we have Lx minus Ly and we have Lx plus Ily. So this gives us Lx square plus Ilx Ly minus Ily Lx plus Ly square. Okay, so we know, so from the lectures you have already seen that L square and Lz are the two main functions that we already know about the eigenvalues. So what we know that L square when operates on LML, we get L plus 1 h bar square LML, and similarly for Lz we know we get ML h bar. So these are the two main relations that we know. So we have to use them, and in order to use them we have to reduce them in terms of these two main equations. Okay, so I'll just shift this thing to the top. Okay, not top, maybe here. Okay, now we know that L square is essentially your Lx square plus Ly square plus Lz square. So we can write Lx square plus Ly square as L square minus Lz square, and this we have a commutator of Lx and Ly, which again we know is your I h bar Lz. So this essentially reduces to Lz square plus, so if you write this I h bar Lz, you have a I square, you get a minus sign, h bar Lz. So now you mainly operate this part on the LML, so you take an expectation value of it. Now since we already know about these eigenvalues, we can use them directly here. What we get, so L square operating on LML gives us L plus 1 h bar square minus Lz square gives us ML square h bar square, and Lz gives us ML h bar. So this is essentially your eigenvalue here. So getting the lambda is then straightforward, you just get a h bar outside. So this was one of the exercise problems that was given in the lecture, so I just thought this would be interesting to solve it. And similarly when you do for L minus, you mainly get a minus here. So I hope this is clear to everyone. If you have any questions, you can ask anytime in between. Just feel free to interrupt me. Okay, so till now we were like looking at the angular momentum operators only. So now what we are going to discuss is the quantum entanglement, which is the main theme of the assignment. Okay, so I'll go to the next page. Okay, so I would like to know what all exactly do you guys know about these quantum entanglement, mixed states? How do you find maximally entangled state? Do you guys already know about all of this? Can anyone say yes or no in the comments? Okay, fine, I'll just go with the very basics. Okay, so yeah, that's what I was also wondering. Since the assignment is based completely on quantum entanglement, so I believed that many people might not know. So I thought I'll go from the basics. How do we actually measure the entanglement? So there is some formula or possibility, like through entropy you measure the entanglement and how you can find the maximally entangled state. And also there are some questions on quantum gates as well, so I'll just show you the basics of quantum gates such that you can use that in your assignments to solve it. So I'm not going to solve any of the assignment questions, I'm just going to give you a brief overview of what these entanglement states are, how do you create these states in, let's say, in real life, how do you make them, and then you can find out. So these are actually very interesting in the present scenario. Quantum entanglement, quantum, like, it's being readily used in quantum computing, so it's a very hot topic at present. Like many big companies like Google and Microsoft, IBM, they are all making, not Microsoft, I think, IBM, Google, they are making quantum computers, and these quantum computers involve a lot of these quantum entanglement features. So let me go through the basics first. So let's say you have a state psi, okay, any state psi, and you have, let's say, the state space as a qubit. You have let's say 0 and 1. So you have, let's say, any quantum system that can be in these two states. Okay, so you define something like 0, 1. Okay, so this is a very generic state. So you already know how you calculate density matrix from this. You get psi, right? So what that gives us, essentially, your C naught square. So I won't waste more time in this. You already know about this. This will be mod C101. There might be some sign mistakes, so just let me know if you find one. And your C1 mod square, which is 1. Okay, so this is a very simple pure state. So what we call as pure state is when you can find the whole okay, in mathematical terms, a pure state simply means, like, if you have rho square equal to rho, that is a pure state. So for example, let's say you have only 0, 0, okay, and you take rho square, you again get a 0, 0. So this is essentially your, okay, so you get a 0, 0. So you call this as a pure state. Similarly, any state in which you find the rho square to be equal to rho is a pure state, and pure state means it's a complete quantum state, okay, where there is no mixture, there is no entanglement. Okay, it's just a pure basic state. Okay, now for in the matrix term also you can easily do it. Let's say you take, so here if we take all of them, so let's say these C naught square and all these coefficients as 1/4. Okay, so you can write them in the form sorry, not 1/4, 1/2. Okay, so the first concern is that the trace of rho should be 1, that you already are aware of. Now on the off diagonal term there can be anything. Now from the first look, can anyone say that if it's a pure state or not? Like, do you have any idea if you can claim it to be a pure state? That means it is not a mixture state or any other entangled. Like this is a single qubit, so there is no question of entanglement at present. But now to find the pure state, you can see. So whenever you can write it in this term, okay, you call it a pure state. So here, sorry about this. So here we essentially have half 0 0 plus 0 1 plus 1 0 plus 1 1, and this you can mainly write from by root 2 0 plus 1 . So you can say this is a psi form. So this is a classical way to find out if it's a pure state or not. But if you get through the mathematical one, you can easily take the rho square. So you had half, you can take the halves out. So you have half 1 1 1 1, and you have another half, which you can take it as 1 by 4 here, and you have 1 1 1 1. So when you do the calculation, you essentially get 2 2 2 2, which is again your rho. So this is a much easier way to see that it's a pure state. Now what is an entangled state? Entangled state is something where you can't really reduce. So before coming to entangled state, I would like to show what is a mixed state, so that you get a better understanding of how to differentiate between a mixed state and an entanglement state. So people often confused with the mixed state and the entanglement state as a similar thing. So mixed state can be for a single qubit as well. So what is a mixed state? For example, when you can't really write in the term of psi. Okay, so let's say you have something of this sort, which you can write as a form 1 by 2 0 0 plus 1 1. So now can you really write it in terms of psi? Does anyone has any idea if you can write this as the form of psi? So I believe no. So this makes it a mixed state where you don't really have the quantumness. So these terms, these off diagonal terms that we had here, these are what we call as coherence terms. So these are the sole feature in the quantum world only. You won't get to see these in the classical world. The diagonal terms are something that we called as populations. Okay, so populations means like you have an atom and there are two states. There is a 0 state and 1 state. Now the probability of being in the ground state or the first state is given by this. You can say this is probability as well. Some call it population of the atom being in the first state or the ground state, and some you can call it the probability of the atom being in the ground state or the first state. Similarly, this coherence term, which are the off diagonal terms of the density matrix, are only present in this quantum world. So when these terms get lost, we say it's like a classical system. So mostly when we have a real quantum system, then there is something called decoherence, which makes the off diagonal terms to be 0, and then we lose the quantumness of the system. Okay, now here you can see that this is a mixed state. Okay, now mixed state is something like whenever you can define your density matrix. So you can actually check here the rho square as well, just for verification purpose. So what you will find, okay, let's take the half out. You will have a 1 by 4 since you have two halves. What you get is 1 by 4 1 0 0 1. It does look similar, but this number 4 was not present previously. So this is actually rho square equal to half of rho, which means this is not a pure state. Okay, and this in return means that you cannot really write in the form of psi. So you can't find any psi such that you can write in this particular form here. Okay, now, okay, sorry, this, now, so I was telling something about, so what's wrong with this? Something's not working. Right, so a mixed state, sorry for the disruption, so mixed state can always be written in the convex summation of pi so this is a generalized form of a mixed state. So whenever you have something of this form, you call it a mixed state. So you, as you can see here as well, so we only have the diagonal term, so you can write this as half 0 0 plus half 1 1, which I have written here. Okay, so this is summation of the states, only the diagonal elements are there. So this you can write in this canonical convex summation form. Now, when do we call it a maximally mixed state? So there is a term as maximally mixed state, which means like that's the mixture is the you can't really go beyond that mixture. It is what you can say a completely classical, it's an ensemble system. So for that, the condition is that if pi, let's say you have a n qubit system, okay, so if your pi is equals to 1 by n, that is all the states have the same probability of occurring. For just like similar to here, you have the 0 state and 1 state having the same probability, half of occurring. If you have the same condition playing here, then you have a maximally mixed state, and we will shortly see how that comes up in the entropy picture as well. Okay, now what is an entanglement state? So till now we were looking at only a single qubit. Now if you let's say you have two qubits, okay, and both can be in the 0 and 1 state, so that means like there are only two possible states, you call it a bit. Okay, and since these are quantum, you call them qubit. I believe everyone is already familiar with the word. Now when you have qubit, let's say this is A and this is B, okay, so there is a Hilbert space corresponding to A and there is a Hilbert space corresponding to B as well. Now when you can write the density matrix such that they are the tensor product of two states, two state space separately, then you call them separable states. For example, if you have something like rho I, you have ij, let's say, you have rho A, tensor product with rho B. So I'll also explain with example. So when you can write in this form where the two state space can be separated, then you call them a separable state. But when you cannot write them in this particular form, then you call them entangled state. For example, I'll show you. Let's say we have for psi A, we consider root 2 a superposition state, okay, and similarly for psi B, we take, let's say, same state you can take, or you can actually generalize it to a random state as well. So let's generalize it to get a better understanding, that will help us. 0 let's say A, or we can just write in the font 0 C1 1. So this is for the A, and we have similarly, let's say 0 for the B. Okay, now the density matrix for the complete system. Okay, now the density matrix for the complete system can be actually given in the form where you have psi A tensor product with psi B, similarly psi A tensor product with psi B. So what I'm saying is the second one is the B part, first one is the A part. So if you write it, so let's say just we find the first half of here with psi B. Okay, so technically, like, you can get a rough idea from the picture as well, diagram. So when you have two states, so let's say it is an atom. Okay, let's consider an atom. So this atom can either be in the 0 state or it can be in the first state, and similarly the second also can be in the in the ground state or the first state, 0 or 1 state, let's say. Okay, so there are 4 possible states that these atoms can fill in, and you can find out through the combination that these are 0 0 0 1 1 0 and 1 1. So these are the 4 possible combinations that the system can be in. So each atom can either be in the 0 state, they can both be in the 1 state, and the either one of them is in the 1 state and another in the 0 state. All the possible combinations are there. So here also, if you do the tensor product, you will actually get all the possible combinations here. So let's say, I think I should put some subscript A here, avoid confusion. Okay, so what we have here is A tensor product with C0 B okay, so what we get, something like so this notation means that they are tensor product. Okay, so I'm just writing with a comma, but it's a many body state, you can say. So there are 2 atoms and it's a 2 body state. You can write it together. So you just, for shorthand notation, you just remove the tensor product symbol and you can write it in this form. And similarly we have other ones. Where the first atom, A atom, is in the ground, that is 0 state, and B atom in the first state, and similarly for the other 2 cases. Okay, so I won't I can just, okay fine, I can write it down. A and the final one. So in this part, both of the atoms are the first state. Okay, so this is the first half, and your density matrix is actually the multiplication, so that will be a very longer part. Now in this you can easily write in the matrix form, so that we will prefer to do here. So in matrix form, what you will have, since you have 4 states, okay, 4 states means the density matrix will be your 4 cross 4, that is that it will have 16 elements. and you have all, let's say 0 0 0 1 1 1 C 1 0. Okay, these are going to have 4 notations, 0 1 0 0, something like this. Okay, so this is the whole density matrix, so that is going to be a very large expression. So we are going to avoid, we are going to skip through it. 0 1, just write few, and you can verify yourself if you want to do. So these are going to be the 4 states. Now how do you see that if it's a let's say entangled state or not? So whenever, let's say for example, let's say take a very simple example. So when you have, let's say, a state that is by 2 0 0 and 0 1. Okay, so I have skipped the A and B here, so you can easily identify these as A and the second as the B. So first number corresponds to the A atom, second number corresponds to the B atom. Now this density matrix you can write in the form of 0. So if you write in the tensor product form, it is much more feasible. You take, okay, sorry, this is not rho, this is psi. So if psi is separable, then rho is definitely separable. So this is a very basic simple example, let's say. So when you have 0, you can write in the form 0 plus 1. So here this part corresponds to the psi of A and this part corresponds to the psi of B. So what you are able to do is you can write in the form, which means they are separable and these are not entangled. Now if you do a very simple mixture, let's say what you do is you consider a state where you have 0 1 and you have 1 0. Now in this case, can you actually see a way that you can find out two different sides? So this corresponds to the A and this corresponds to the B, as I said previously. So I'll just break it down in this form here, which makes it look easier. So now can you tell me if you can write this part in the form of psi A tensor product with psi B? Is that possible? You can say anything, yes, no, it doesn't matter. The right answer is obviously appreciated, but just for your understanding, I just want to recheck if everyone is following it. If you have any questions, you can just ask me in between. Okay. Hello, is everyone here? Okay, so I'll just continue with it. Okay, so in this case you can see that you can't really write in the tensor product form, because this you like here you could actually take common the 0 and you have the tensor product of 0 plus 1 on the other side. But here you can see that you can't really take anything common here. It's 0 on this side and 1 on this side, and similarly for the B atom we have 1 and 0. So you can't really take anything common here. I'll just check if there's anything on the chat box. Okay. Yeah. So this is something that you call an entangled state. Okay, you can't really differentiate between the two, and there are some states which are even more complex, so you can't really So if you have, let's say this is a row, psi you have, okay, so you can write this row as psi. So this is a pure state here, okay, pure but entangled state. Now you can actually choose some states which are not pure and entangled, and they are much more complex. For example, I'll just give one example here. So let's say you consider a, so these had root 2. Let's say you consider a density matrix in the form 0 0 0 1. So you have seen previously that there are all type of possibilities that can happen, okay. So if you consider such case, then you will be able to see that you can't really, so these are, first of all, you can't really write in the form of psi, and secondly, if you have let's say write in the form of tensor products as well, you will be able to see that you can't really write in the common notation as well. So you can't get anything out of it. It's a completely entangled state. Now, in physical sense, what does entanglement means is that, let's say you have two atoms, okay, and they have this 0 and 1 state. So let's consider an entangled state, okay. So this is one of the entangled state. Now if you so when you have a pure state, when you do a measurement on one system, let's say there are two atoms A and B, you take measurement on A, it doesn't really affect the B at all. But when you have an entangled state like this, okay, and you take a measurement on just the first atom, it automatically affects the second atom, okay. So if you have, let's say, pure state, that is, let's say you have a 0 0 plus 0 1, in that case you had a 0 cross 0 1, and if you take a measurement on this atom A, then you get to know that it's 0, but you don't really get any information about the second atom, okay. But here, if you make the measurement on the first atom and you find that it's in 0, automatically the second atom you get to know that it's in the 1 state, okay. So this is what the entanglement does. So whatever you do on one atom, let's say you take any kind of measurement or do anything with the first atom, it will automatically affect the second atom as well when they are entangled. So this is a very interesting property in quantum world. So like even Einstein had this notion of a spooky action at a distance. So it's like you have an atom on Earth and you have another entangled, you make them entangled, and you put the other atom somewhere in the moon, and you do something here, and instantaneously the other atom gets affected in the moon. So which was for Einstein not really believable, because something happening instantaneously means that it's breaking the law of speed of light, right? So it's the information is traveling faster than the speed of light. So this is the power of quantum world. So if you have a entangled state, so there was one question in your assignment as well based on the quantum teleportation, in which if you so I won't really solve it, but I can give you a rough idea. So if you have let's say 3 qubits, okay, and let's say there usually it is said in context of Alice and Bob. So Alice wants to send a, let's say, a quantum state to Bob. Then what he does what she does is that she has a quantum state psi, and this they are going to entangle. So there is a protocol, you will have to do it for your assignment itself. So you have to make the 2 qubits entangled, and then you have to make some measurements on these qubits such that when you tell Bob about the key that the measurement you have obtained, based on that key, the Bob can actually reproduce the same state. Okay, so this is one of the most powerful tools of quantum entanglement in this whole quantum system world. Okay, now in order to find, let's say, maximally entangled state, how do you find? So there is actually a measurement. I'll tell you the formula is of entropy, through which you can find if the state is like, just for example, we saw for rho square, if rho square comes out to be rho, then we know that it's a pure state and not a mixed state. Similarly, there is this equation or you can have rho b or in the summation of pi log n pi. So this is what we call as von Neumann entropy, and if this entropy gives you 0, that means it's a pure state and not entangled. Okay, so as I said previously, there can be possibility of having entangled states and still being pure. Okay, and now if you have E psi is not equal to 0, that means it is entangled. And if you are looking at the individual, so this is partial tracing over the system. Let's say you partial trace over B and you get the information about A, or you do partial tracing over A and you get information about B. And in that case, you get the information about if it's a mixed state or a pure state. Okay. And when you have E of psi equal to 1, in that case it is maximally entangled state. And for particular system, it's a maximally mixed state as well, a particular qubit. So this is something that you can use. So there are endless number of entangled states you can create mathematically in your notes, and you can check using this formula if this actually gives you a maximally entangled state or just a normal entangled state, and if it's a pure state or not. Okay, so we can actually take some examples here as well. So let's say you take some okay, for example, you have, let's say we take the same that we took previously. So we had, let's say 0 1 1 0. Okay, now if or let's say we take the 0 0 and 1 1 and we just do a check. Okay, you can do for any other qubits as well. So if you take this, now this is okay, this formula is also very important. This is something called Shannon entropy, which is very famous in quantum information. So this means that if you have the terms in the diagonal, okay, so the diagonal terms, you take the probability of the diagonal terms and you just take the sum over. Okay, so here for example you get E of psi, so you can say that these are actually the diagonal terms. You have 1 by root 2 and all 0, right? Okay, so first of all you need to, this is not a square matrix. You have to first find out the row, which is your 1 by 2 0 0. Okay, now you can see that these two are the diagonal ones and these are the off diagonal ones. So we only take the probability for the diagonal ones. So these are the coherence terms, and we take the probability of the population terms. Okay, so what you do is, to calculate A of psi, you have half of for both. So you take half log base 2 half minus half log base 2. So here one important part I missed. So this n, I'll use different color. This n corresponds to the number of qubits that you consider. That's the dimension of the system, maybe you can say. Okay, so here we have only 2 qubits, so we take 2, and what you will get here, so these 2 are same, so half gets add up, you have log 2 of half, or the minus gets in and you get a 1. So this is one of the, you can say, an example of a maximally entangled state that we just looked up. Okay, similarly you can find, let's say you take a very simple matrix that we have already found out to be pure states, and let's verify if it works there also. Okay, so a very basic simple pure state would be, let's say, 0. Okay, that's just in a ground state. So your rho makes it 0 0, and for here we only have 1 0 0 0, which is a very basic pure state. You can also take the one which was complex, half of. So here it is evident from the fact that log 1 gives us a 0, because there is only one state, there is no half or anything else. So this is essentially gives us a 0, that means a pure state. But for this case, this is a much more complex case. So when you have, let's say, rho, so you can't really do it directly, but you need to go to the eigenbasis of it. So in order to find in the form of this, you have to take the eigenbasis of it. So what you will get if you do the eigenvalue calculations, you will have an eigenbasis 1 1 with root 2, and other one as 1 by root 2 1 minus 1, and in that eigenbasis, when you write it, you will essentially have the vector written in this. Okay, so this can actually be, wait, so the main wave function was, and this essentially corresponds to the particular eigenvalue, and once you have this particular eigenvalue, you can actually write it as a plus state. So let's say this eigenvalue is a plus and this eigenvalue is a minus state. Okay, so what you have is again a pure state, just like 0 0. This is your density matrix, and again you get the same log 1 minus, and this gives you a 0. So this essentially tells you, this is not rho, this is S of E. So you can use this formula. So this is a very powerful tool. This is a very powerful tool, and you can use this to find the entanglement of any system of consideration, whatever you require. So to find out the maximally entangled states in your assignment, you can use this, as well as you can use other features that you already are aware of. So this is one of the examples that you can consider. Now, so next I'm going to show some of the quantum gates. So you might require these quantum gates. So I saw a few questions that relates to the quantum gates, how you get the results of the quantum gates, or even for the quantum teleportation protocol, when you are deriving or you're making the circuit of the quantum circuit for the quantum teleportation, you will need to use the quantum gates. So what are quantum gates? Now quantum gates are like these are unitary operations that you operate on any qubit. So let's say you have a qubit here, so this is a psi, okay, and you operate a gate on this. So there can be a single bit gates as well as 2 qubit gates, okay. So I'll come to the 2 qubit gates after this. So this is something like a unitary operation, and you get a u of psi in the output. So you are already familiar with the gates in your classical sense, like there are AND gates, NAND gates, CNOT gates that we use in the analog computation, analog or digital computations. So these are similar gates but in the quantum circuits, okay. So for example, if you have something called a Hadamard gate, what this does, so if you put H on 0, you get a superposition state, and similarly for 1 you get a minus. So this is a gate that one uses to form the superposition, and we have seen that how superposition can be very useful. So in classical qubits, this is the part that is lacking. So you can't have superposition states, either you are in the 0 or you have 1. And these superposition is what makes the quantum computers much more powerful compared to the classical ones. Now similar to this, you have the poly gates. So if you, let's say, apply sigma x on 0, you get a 1, and similarly if you apply a sigma x on 1, you get a 0. So this is also called the bit flip. You are changing the bit, or in classical sense you can say it's a NOT gate. So if you have a 0, the NOT gate changes it to a 1. If you have 1, the NOT gate changes it to a 0. And similarly all other poly operators like sigma z, sigma y. So sigma z does nothing special for 0, but for 1 it changes the sign, so it has a negative eigenvalue for 1, okay. So these are some of the single bit gates, and some major 2 qubit gates that can be useful for you for your assignments can be, first of all, the CNOT gate. So this is one of the most powerful gate in the whole quantum computing, okay. Now what the CNOT gate does is, like, if you have 2 qubits, okay, you have A and B, and there is a control qubit which changes or flips the other qubit. For example, let's say you have 0. So when it's 0, and this psi is, let's say, is a superposition of let's say not exactly a superposition, maybe a superposition of let's say CA, a generic superpositions of CB of 1. So you don't really know the probability, it's not like half for both, okay. And in that case, if the A is 0, then your state initially was 0, CA 0, CB 1, right? Now once you apply this CNOT gate onto this psi, what this does is that because it's 0, it does not really do anything on the other side, okay. So it keeps it as it is. But if it would have been 1, then 1 flips the bit, that is, it changes, okay. So control means you are switching it on and off. So when you want to flip the bits of the other qubit, then you initialize the state in 1 and you do the control not, and if you don't want anything to be affected, then you just keep it 0, okay. So a 0 means like that qubit is not really present, it's not doing anything, but a 1 is actually making it an entangled state. So this is the reason why C0 gate is the most powerful. So it is actually creating a entanglement state. So for example, let's say you have a for psi A you have 1 by root 2 0 plus 1, and for psi B also you have, let's say, 1 by root 2 0 plus 1. Okay, so this is very generic state, and your total psi that you get is from the tensor product psi A psi B. Okay, and what you get is your 0 0 0 1 1 0 and 1 1. So till now it's a pure state. You can easily take the common things out. So like here you have 0 tensor product with 0 plus 1, and here you have 1 tensor product with 0 plus 1, and you take the common out, you get a 0 plus 1. So this is what we started from essentially, so it doesn't make sense to redo it. Now what happens when you put the C0 gate onto the psi, when you operate it on the psi? So this is our psi essentially. So wherever there is 0 on A, it doesn't do anything. So your 0 0 and 0 1 remains the same, but when it operates on 1, so it changes the feature completely. So it makes it 0 1, and this makes it 1 0. Okay, so now can you actually do this separation? Can you make it in the form psi A cross psi B? So if you actually look at it, you have something like 0 tensor product with 0, so this is, let's say, 2, you take it out, you have 0 plus 1, but on the other side you have 1 tensor product with 0. So now it's not separable anymore. So what did it do? It is that it generated an entangled state. So in quantum circuit, in order to generate entangled state, you can do different features, and one of the prime gate is this operation, the C0 operation, that gives you an instant entangled state. So whenever it is 0, it doesn't do anything, but whenever it is 1, it flips the bit, and this creates an entanglement state. So this is one of the most easy way to create an entangled state in a quantum system. Okay, and some other gates that might be useful for you is a swap gate that is also used. So what does swap gate does? So when you are okay, so when you are 0 0, it doesn't really do anything, it's remain as it is. But when you have 0 on the first bit and 1 on the second bit, then it flips it. So the A system goes to the 1 and B goes to 0. It's like the complete opposite of what you were initialized. And similarly for 1 0, it's just the same thing, 0 1, and for 1 1 it doesn't do anything. Okay, so these are some of the gates that can be useful. So you can create a superposition using the Hadamard gate. You can flip the bits, so whenever you want to do any operations, let's say you want to flip one bit and you do a sigma x or sigma z. So these are the main gates that are required in the quantum computing world, and one of the most important is the C0 gate that can give you an entangled state. So if you have any questions, you can ask, or I believe we will end this session here. Okay, so thank you all for coming this session. So take care, goodbye.